Thermodynamics. Introduction. One of the most vital manifestations in nature is the energy which accompanies all physical and chemical transformations. The versatile phenomena like fall of a stone, motion of a billiard ball, burning of coal, working of engines, photosynthesis in plants, growing of living beings, all these involve absorption, evolution, and redistribution of energy. The most common form in which energy appears is heat. Thermodynamics is a theoretical method which can be applied to the process involving absorption, evolution, or transfer of heat. The word thermodynamics means study of flow of heat because therm means heat and dynamic means movement. However, as we move further, it will be seen that the subject involves a more general quantity, that is energy. Besides it, there are many other forms in which energy appears, like mechanical energy involved in the motion of machines, electrical energy exhibited by flow of electron in a conductor, radiant energy, invisible light and radiations in general, and finally chemical energy, the energy stored in all substances and which appears when substances undergo transformation. All these forms of energy may seem distinct but may be transferred into one another certain conditions. A study of this interrelation of various forms of energy in a system constitutes the subject of thermodynamics. Thermodynamics may be defined as the branch of science which deals with the quantitative relationship between heat and other forms of energy. When energy changes accompanying the chemical process, it is referred to as chemical thermodynamics. Thermodynamics is primarily based upon three fundamental generalizations called the first, second, and third law of thermodynamics. These laws have been arrived at purely on the basis of human experience. In addition to these laws, there is another generalization which was put forth at a later stage and is known as zeroth law of thermodynamics. Though there is no theoretical proof of this law, the predictions based upon this law has been verified and no contradiction have been reported so far. In general, zeroth law provides the basis for the measurement of the first law deals with the equivalence of various forms of energy. Second law deals with the direction of the given chemical process. Third law deals with the evaluation of thermodynamic parameter like entropy. Scope and objectives of thermodynamics. The importance of thermodynamics lie in the fact that it provides explanation of macroscopic property, that is bulk properties of matter. In terms of microscopic concept of matter, thermodynamics deals with chemical energetics, that is the study of energy changes during chemical reactions. Thermodynamics and chemical energetics find application not only in chemistry but also in other branches of science like engineering and technology extra. Some of the ways in which thermodynamics can be useful are as follows. First is to predict the spontaneity of or feasibility of a process. Thermodynamics helps to predict whether a given physical or chemical process is feasible under the given set of conditions. Second is to predict the extent of reaction. Thermodynamics can predict the extent up to which reaction can proceed before the equilibrium is attained. That is, it can help to determine the yield of a chemical reaction. The third one is to deduce some important laws of physical chemistry. Some important laws of physical chemistry, such as Rolle's law, Onso law, distribution law, phase rule, etc., can be deduced from the laws of thermodynamics. Third is the limitation of thermodynamics. It studies the properties of matter on the macroscopic scale, that is, the system involving very large number of molecules. The law of thermodynamics are not applicable to individual atoms, molecules, or ions. So thermodynamics does not give an insight to the structure of matter. It gives the relationship between various experimentally observed properties, but it is unable to give the actual values of these properties. Also, it does not explain as to why these properties arise in a system. It can predict the flexibility of the process but doesn't give any information regarding the time taken for the process to complete and the rate at which process takes place. It is concerned only with the initial and final states of the system. It fails to tell the path by which the process is carried out. Hence, it doesn't throw any light on the mechanism of the process. Some common thermodynamics terms. First, system boundary and surrounding. A system is defined as the part of universe under investigation separated from the rest. Call the surroundings by real or imaginary boundaries in order to study the effects of variables such as temperature, pressure, volume, etc. upon its contents. The remaining portion of the universe other than the system which may be capable of exchanging energy and matter within its called surrounding. So universe is equals to system plus surroundings. The system and surroundings are separated by a real or imaginary surface called boundary. The boundary defines the limits of a system. The system and surroundings exchange matter and energy through this boundary. Considerable more of a gas confined in a cylinder fitted with a piston. The gas constitutes the systems, the cylinder, piston, and everything outside the cylinder from the surrounding. Next is types of system. On the basis of exchange matter and energy with the surroundings, there are three types of systems: open system, closed system, and the isolated system. The third is homogeneous and heterogeneous system. Homogeneous system, when a system is completely uniform throughout, it is called a homogeneous system. A homogeneous system has only one phase. For example, a pure solid, a pure liquid, a solution of two completely miscible liquids, a mixture of gases. All the system have only one phase, so that the system is uniform throughout. Hence, it is said to be homogeneous. Heterogeneous system. If a system is not uniform throughout, it is called a heterogeneous system. In other words, a heterogeneous system consists of two or more phases which are separated by a boundary. However, each phase in its own is uniform. Ice cubes in a glass, water, a mixture of oil and water, a mixture of iron filings and sand are few examples of heterogeneous system. Following are general examples of heterogeneous system: a mixture of solid and vapor, a mixture of solid and liquid, a mixture of two or more solids, a mixture of two or more immiscible liquids. Next is macroscopic system. A system containing a large number of particles, atoms, and molecules is called a macroscopic system. Fifth is macroscopic property. The property of a system associated with the bulk behavior of large number of particles in macroscopic system is called macroscopic property of the bulk or bulk property. These properties are pressure, temperature, volume, composition, viscosity, density, etc. For example, in order to know the temperature of water, we don't deal with individual molecule, but we consider the molecule in bulk. So temperature is a macroscopic property. Macroscopic properties can be divided into two types: extensive property and intensive properties. Extensive properties, the property of the system which depend on the quantity of the matter present in the system, are called extensive properties. So common examples of the properties are mass, volume, internal energy, enthalpy, heat capacity, etc. Second is intensive properties. The properties of the system which are independent of the quantity of the matter present in the system are called intensive properties. Temperature, pressure, refractive index, viscosity, specific heat density are some common intensive properties. State of a system and state variables. State of a system. The state of a system refers to the condition of a system where it is in macroscopic properties have definite values. When any of the macroscopic properties PVT, SH, etc. of the system changes, the state of the system also changes. In any process, it is important to mention initial and final states of a system. State variables. In a thermodynamic process, it is necessary to describe the state of a system before and further it undergoes the process. The initial and the final states of the system can be described by specifying a certain number of macroscopic properties. The macroscopic properties required to describe the state of a system are called state variables. Thermodynamic equilibrium. A system in which the macroscopic properties in different parts of the system don't undergo and change with time is said to be in state of a thermodynamic equilibrium. In other words, it in the state of thermodynamic equilibrium, the state variables in various phases have constant values. Now, the criteria for thermodynamic equilibrium. To be in the state of thermodynamic equilibrium, the system must attain three types of equilibria simultaneously. These are thermal equilibrium, chemical equilibrium, and mechanical equilibrium. Thermal equilibrium: a system is said to be in thermal equilibrium if no heat flows from one part of the system to another. This can be achieved if the temperature remains constant throughout the system. Mechanical equilibrium: a system is said to be in mechanical equilibrium if not mechanical work is done by one part of the system on other part of the system. It implies that there is no movement of matter within the system or between the system and surroundings. This is possible if the pressure remains constant throughout the system. Third is chemical equilibrium. A system is in the state of chemical equilibrium if there is no change in the composition of various phases in the system. In other words, if the composition of different phases in the system remains same throughout, the system is said to be in chemical equilibrium. Now, the thermodynamic process. A thermodynamic process may be defined as path of change of a system from one equilibrium state to another, which is usually accompanied by change in energy and/or mass. A thermodynamic process may be classified into different types depending upon the conditions under which the change of state is brought about. These are isothermal process. A process is said to be isothermal, which is carried out in the manner so that the temperature of the system remains constant during each stage of the process. Adiabatic process. A process is said to be adiabatic when the system does not exchange heat with the surroundings, that is no heat flows from system to surrounding or vice versa. Isobaric process. A process is said to be isobaric if it is carried out at constant pressure. For an isobaric process, dP is equal to 0. Most of the reactions carried out in laboratory are at constant pressure. Next is isochoric process. A process is said to be isochoric if it is carried out at constant volume. For an isochoric process, dV is equal to 0. Cyclic process. It is process in which the system returns to the original state after undergoing series of changes. For a cyclic process, du is equal to 0 and dH is equal to 0. For example, Carnot cycle. Reversible process. The term reversible refers to the path in which the process is carried out. A reversible process is the one which is carried out infinitesimally slowly through a series of steps so that the system remains almost in equilibrium state and the process can be reversed at any stage be infinitely small changes in external conditions. In other words, a reversible process may be defined as a process which is conducted in such a manner that at every step the driving force is infinitesimally greater than the opposing force and the process can be reversed by an infinitesimal increase in the opposing force. Such a process which is carried out in infinitesimally small steps and can be reversed by infinite small changes in external conditions is called reversible process if we keep on removing sand particles one after the other. Next is irreversible process. A process which does not fulfill the requirements of reversibility is called irreversible process. In other words, an irreversible process does not take parts infinite slowly. Such process goes from initial to final state in a single step in a finite time and it can't be reversed without the help of external agency. Here is the difference between reversible and irreversible process. A reversible is very slow occurring through a series of equilibrium states. An irreversible process proceeds with a measurable speed. The driving force is infinitesimally greater than the opposing force. The driving force is much greater than the opposing force. A reversible process can be made to go in either direction. An irreversible process can proceed only in one direction. It is in equilibrium at all stages. Equilibrium exists in the initial and final stages only. A reversible process can be brought back into initial state without producing any permanent effect in the surroundings. An irreversible process can't be brought back to the initial state without avoiding a permanent change in the surroundings. Work obtained is maximum in a reversible process. Work obtained is not maximum. It is difficult to realize in practice, but reversible process can be performed in practice. Now, the modes of exchange of energy. Chemical reactions are accompanied by the energy change. The exchange of energy between the system and surroundings can occur in several ways. Two important modes which a system can exchange energy with the surroundings are heat and the work. Heat. The exchange of energy takes place as heat if the system and surrounding are at different temperature. So, heat is the quantity of energy which is exchanged between the system and surrounding when they are at different temperature. If the system is at higher temperature than the surrounding, then heat is lost to the surrounding. If the temperature of the system is lower than the surrounding, then heat is gained by the system. The amount of heat gained or lost by the system is represented by U. Sign convention of heat. When heat is absorbed by the system from surroundings, it is given positive sign. When heat is lost by the system to the surrounding, it is given as negative sign. Units of heat. The unit of heat that was often used is calorie. A calorie is defined as the quantity that required to raise the temperature of 1 gram of water by 1 degree Celsius in the vicinity of 15 degrees Celsius. The SI unit of heat is joule. Now the work exchange of energy between system and surrounding can occur in the form of work. Work may be mechanical work, pressure, volume work, electrical work and gravitational work. Mechanical work is said to be done if the point of application of force move in the direction of the force. In other words, work is defined as the force multiplied by the distance through which the force acts. That is, work is equal to force into distance. Electrical work is defined as the product of electromotive force and the quantity of electricity flowing through the circuit. Gravitation work is said to be done when an object is moved against the gravitation force. It is defined as the weight multiplied by the height through which through which is with which it is moved. Hence, gravitation work is equal to weight into height. Pressure volume work. This type of work is called the work of expansion and is the most important type of work in thermodynamics. It is significant in system which consist of gases and involve changes in volume against the external pressure. Pressure volume work is said to be done when a gas expands or contracts against external pressure. Here's the state functions, path functions, and their differentials. A state function is a thermodynamic property of the system whose change in values depends only upon the initial and final states of the system and is independent of the manner by which the change is brought about. Some common state functions are internal energy, enthalpy, entropy gives free energy, pressure, temperature, volume, mass. The change in the value of these state functions depend only upon the initial and final state of the system and not on the path by which the change from initial to final state is carried out. For example, if UA represents the internal energy of system in state A and UB that of state B, then the change in the internal energy value in going from state A to B is given by del U is equals to UB minus UA. On the other hand, the property of the system whose change in value depends only upon the path followed by the process called path function. Two very important properties, namely heat and work, were not the stable functions because they are path dependent, hence heat and work are path functions. There is an important mathematical feature associated with state and path functions. A thermodynamic process is often considered as made up of number of small steps. The total change in the value of thermodynamic property can be obtained by integration only if it is a state function. Also, a thermodynamic property can be differentiated only if it is a state function. In other words, the differential of state function is a complete differential or exact differential. For example, internal energy U is a state function and a small change in internal energy can be represented by del U. In the case of du is a complete differential. This differential du may be integrated between the limits of initial state A and the final state B of process to obtain the definite value ub minus ua or del U. To conclude, we can write that all the state functions are complete differential or exact differential, whereas path functions are inexact differentials. Now, the zeroth law of thermodynamics. The zeroth law of thermodynamics is known as the law of thermal equilibrium. This law was formulated much later than first and second law of thermodynamics, still in precede these law because of its prime importance, and it is called zeroth law. This law provides logical basis for understanding the concept of temperature. This law is based on common observation. Zeroth law is stated as when two bodies are in thermal equilibrium with the third body, then in turn also in thermal. When two bodies are in thermal equilibrium with the third body, then in turn are also in thermal equilibrium with each other. Following illustration has to understand this law. Consider two bodies A and B which are separately in thermal equilibrium with the third body C. When the bodies A and B are replaced in contact with each other, they also be in the thermal equilibrium. All the three bodies A, B and C are in thermal equilibrium, so they have the same temperature T. Utility of zeroth law. The common use of thermometer for comparing the temperature of two or more systems is based on the zeroth law. For example, if you want to compare the temperature of any two bodies, say A and B, then the thermometer may be considered as body C. As in the above illustration, the thermometer is always to come into thermal equilibrium with body A and then with body B by placing it in contact with A and then B. The temperature readings on the thermometer give the comparative hotness of bodies A and B. As the size of thermometer is small, so it is considered that there is a insignificant role of heat from bodies A and B when they are placed in contact with thermometer, so the recorded temperature gives the accurate reading of hotness of the body. Now, the first law of thermodynamics, it is a common observation that energy can't be generated without using energy of same kind. If whenever the energy of one kind is produced, an equal amount of some other kind of energy disappears so that the total energy of the universe remains constant. It has been long accepted by the scientists that it is possible to construct a perpetual motion machine, that is a machine which can produce energy without consuming energy. All these observations point to the fundamental idea of conservation of energy. So the first law of thermodynamics is basically the law of conservation of energy, which states that energy can neither be created nor be destroyed, although it can be converted from one form to another. This law of conservation of energy is purely based on experience and has been studied in a number of ways. Some of its other statements are the total energy in an isolated system must remain constant, however, it may change from one form to another. Whenever a certain amount of energy of one form is consumed, an exactly equivalent amount of energy of some other form must be produced. It is possible to construct a perpetual motion machine, that's a machine which can produce energy without consuming energy. Now, the corollary of first law of thermodynamics, equivalence of heat and mechanical work, follows as consequence of the law. Suppose that there is no equivalence between mechanical work done and the amount of heat produced. Suppose a certain amount of heat, say x joule, is converted into work. Note now the process is reversed, and say y joule of heat is produced. The amount of heat produced, y is not equals to x. It is either less than x or more than x. If y is less than x, then heat energy equals to x minus y is destroyed, and if y is greater than x, then heat equals to y minus x is created. If the process is continued in cycle, heat energy can be continuously generated and a perpetual motion machine can be produced. So if we assume that there is no equivalence between heat and work, then either heat is destroyed or created in this process, but such observation is denied by human experience. It is against that very essence of first law of thermodynamics, which established conservation of energy. Hence there must be exact equivalence between heat and mechanical work. The internal energy is the energy a system possesses because of its temperature, volume, pressure, and chemical composition. It is known as internal energy or intrinsic energy, and it is designated as U. The heat supplied at constant pressure is equal to changes in another thermodynamic property called the enthalpy or heat constant. Enthalpy is the total energy associated with a system, which includes its internal energy and also energy due to external factors such as pressure, volume, conditions. Specific heat capacity. Heat capacity is an extensive property because the amount of heat required Q to raise the temperature by del T depends upon the quantity of substance. For example, a large block of copper metal has to a higher heat capacity than a small piece of small metal. Specific heat capacity or specific heat is the quantity of heat required to raise the temperature of 1 gram of substance through 1 Kelvin or 1 degree Celsius. Now, the molar heat capacity. Molar heat capacity of a substance is the quantity of heat required to raise the temperature of 1 mole of the substance through 1 Kelvin or 1 degree Celsius. Molar heat capacity, Cm is equals to heat capacity divided by molar mass.